Before we dive into vector functions, it's important to make sure you're ready for what's coming next. If you haven't already, I strongly recommend watching 2 early lessons from this calculus playlist: Equations of a Line in 3D Space and Parametric Equations. They will give you the background you need to follow everything smoothly in this lesson. Once you are ready, make sure to leave a like, subscribe, and turn on notifications so you don't miss the next lessons in this vector function series. Your support helps our channel grow and keeps us creating quality content. Thank you. Okay, let's begin. What is a vector function? In regular calculus, we study functions that take a number and return another number. For example, f of x equals 1 plus x tells us for each input x, the output is x plus 1. So if x equals 1, then f of x equals 2. But what if a function could give us not just a number, but a point for every value of a parameter t? That's exactly what a vector function does. It describes motion, geometry, and direction all at once. A vector function takes a single number t, often representing time, and returns a vector, a position with x, y, and z components. You might say, well, even f of x gives us a point on the xy plane. And that's true. But real motion happens in 3 dimensions. That's why vector functions are the perfect tool for describing how things move through space. While we always strive for comprehensible explanations, we won't sacrifice precision. We don't do shortcuts on this channel, especially when it comes to definitions. To build a solid foundation, let's start with the formal, rigorous definition of vector functions. In mathematics, a vector function can be seen as a path in space. R vector is a function from the subset U to the 3-dimensional space. The domain U is a subset of the real numbers, and the 3-dimensional space is the codomain. That means we take numbers from some interval U, often values of a parameter t, and each one gives us a vector in 3-dimensional space. The set C of terminal points R of t for t an element of U is called a space curve, and the path R is said to parameterize C or trace out C. That means, as t changes, the tip of the vector moves through space, tracing out a curve. We call that curve a space curve and say the vector function parameterizes it. If the function has only 2 components, all its points lie in a plane curve. So, in short, a vector function is like a motion rule. It takes a single number and turns it into a position in space, tracing a continuous path as t changes. Let's look at some simple examples. Sketch the curve represented by each vector equation. First, we create a table of values. To find the values for each line, substitute the value of t into the x, y, and z components. Plot the points in 3-dimensional space. The table shows the path of a particle, or the points that trace the curve. The function we are working with is a vector equation for a straight line in 3D space. The second example is the classic equation for a circular helix or spiral. This example is great because it demonstrates how to graph a path in 3D space using trigonometric and linear components. Here is the table of values for t from 0 to 2 pi, using key angle values where cosine and sine are simple. We will approximate the numerical values for better visualization. Let's focus on the role of each component. The components cosine and sine of t are responsible for the circular motion. Since cosine squared plus sine squared equals 1, the projection of the curve onto the xy plane is a circle with radius 1. This establishes the rotational movement. The component z equals t is responsible for the upward movement. As time t increases, the particle spirals up the z-axis. Combining the two movements creates a helix, or a screw shape, that starts at 100 and completes one full revolution by the time it reaches a height of z equals 2 pi. This function traces out a beautiful helix in 3D space. As t increases, the point spirals around the z-axis while simultaneously moving upwards. Let's summarize. A vector function assigns a vector to each input t. Its components x, y, and z describe the coordinates of a moving point. The path traced by tip of that vector forms a curve, the geometric picture of the function. A vector function is essentially the same thing as three scalar functions. A vector function is the first step toward describing motion, direction, and change in space. In the next episode, we will take the derivative of a vector function and discover how velocity and acceleration emerge naturally from calculus in space.